Hi everyone. In this lecture, I will introduce different proof methods and we will cover sections 2.4, 2.5, and 2.7 of the textbook. So we'll start with some preliminary definitions. First, let's start by defining a theorem. A theorem is a statement that can be proven to be true. How can we prove it? By presenting a proof. What is a proof? A proof consists of a series of steps that each one of them follows logically from assumptions or from previously proven statements or from previously proven theorems and lemmas, and the final step should result in the statement of the theorem being proven. And also we define axioms. Axioms are some statements that we assume to be true, but we don't provide any reason for that. We just assume that those statements are true. So here is a theorem and its proof. Uh, the theorem says every positive integer is less than or equal to its square. And we're going to prove that this statement is a tautology, which means that it's always true. As you see, this statement is a universally quantified statement. So it basically means that for every integer x, that integer is less than or equal to its square, which means that x is less than or equal to x squared. So this is the universally quantified statement that we are going to prove that is true. So if you remember from the previous sections in this chapter, we said first we need to use a universal instantiation and assume that x is an arbitrarily chosen integer that is an element of the domain. What is the domain here? It's the set of all positive integers. Why? Because in the statement, in the theorem, we say every positive integer, which means x belongs to a set of all positive integers. So as you see in the proof, the first statement that we say is, let's assume that x is an integer that is greater than 0, which means let's assume that x is an element of the set of all positive integers. This is basically a universal instantiation because x is arbitrarily chosen. Now, since x is an integer and x is positive, we can say x is greater than or equal to 0. I'm sorry, greater than or equal to 1, because there is no integer between 0 and 1, right? So if x is greater than 0 and there is no integer between 0 and 1, so it should be either 1 or it should be greater than 1. That's why we write x is greater than or equal to 1. Now, since x is positive, we can multiply both sides of an inequality by x and keep the direction of inequality the same. So in algebra, you know that if you have an inequality and you multiply both sides by a positive integer, you can keep the direction of inequality as it is. But if you multiply both sides of an inequality by a negative number, then you need to reverse the direction of that inequality. But in this case, since x is positive, when you multiply both sides of this inequality, you don't need to change the direction of the inequality, and we get the following inequality. X squared is greater than or equal to 1 times x, which simply means that x squared is greater than or equal to x. So this is the end of the proof, and usually we represent the end of the proof by a symbol which you see here. You know, this is a solid black square that you see at the end. So at the end of the proof, we use the rule of inference that we saw before, which is called the universal generalization. We say, okay, x was an arbitrarily chosen element of the domain, and x squared is greater than or equal to x. Therefore, we have proven that this universal statement for every x is less than or equal to x squared, is true. So remember, at the beginning of the proof, we assume that x is an arbitrarily chosen element of the domain, which is a universal instantiation. And at the end of the domain, we say, since x squared is greater than or equal to x, and x was arbitrarily chosen, therefore the universal statement that we wanted to prove in the theorem has to be true. So we are done with the proof of the theorem. So let's introduce a number of proof methods. The first method of proof that we introduce in this lecture is proof by exhaustion. Proof by exhaustion means that when you have a universal statement and you want to prove it, if the domain is finite and the domain is small, then you can prove the claim for every element of that domain, and this way you prove the universal statement for that small domain. So if the domain of a universal statement is small, it may be easiest to prove the statement by checking each element individually. That's why we call it proof by exhaustion, because it's an exhaustive process. You have to prove the claim for every single element in the domain. A proof of this kind is called a proof by exhaustion. So we will see different examples of this method, but let's introduce another method of proof. This one is called disproof by counterexample. Basically, using counterexample, you can prove that a universal statement is false, or you can disprove a universal statement or a universally quantified statement. A counterexample, as we saw before, is an assignment of values to variables of a universally quantified statement that shows that the universal statement is false. So if you have a universal statement and you replace the variable of that statement with a value that makes the predicate of that statement false, the conclusion is that universal statement is false, and it cannot be true because it is false for at least one element in the domain. So in this slide, I'm going to show you an example of proof by exhaustion. Let's assume that we are going to prove that for every integer that is greater than or equal to 0 but less than 3, n plus 1 squared is greater than n cubed. So in this theorem, the domain is very small. We only have 3 elements in the domain, 0, 1, and 2. So instead of proving that inequality in a general manner, we only need to prove it for 3 integers, 0, 1, and 2. So this is a good opportunity to use proof by exhaustion. As you see here in the proof by exhaustion, we need only 3 statements. When n is 0, then n plus 1 squared is 0 plus 1 squared, which is 1. And n cubed is 0 cubed, which is 0. And since 1 is greater than 0, therefore the inequality is true for the first case. In the second case, when n is equal to 1, then n plus 1 squared is 1 plus 1 squared, which is 2 squared, which is 4. And n cubed is equal to 1, and obviously 4 is greater than 1. In the last case, when n is equal to 2, as you see, n plus 1 squared is 9, but n cubed is 8, and the left hand side, which is 9, is greater than the right hand side, which is 8. Since we proved the inequality for every element in the domain, therefore the universal statement that we were going to prove is true. So that's an example of proof by exhaustion. We have seen different examples of this proof by counterexamples in the previous chapters, but here I'm going to show you one easy one. Every month of the year has 30 or 31 days. That's the statement that we are going to disprove. To disprove it, all we need to do is finding one month that doesn't have either 30 or 31 days. February is a counterexample because February has either 28 or 29 days depending on whether we are in the leap year or not. So this is an example of a disproof by counterexample. Basically, in this kind of disproof, we are dealing with a universal statement, and we are finding a counterexample to that universal statement, and this way we can simply say that that universal statement is false. So far we have seen two methods of proofs. One was proof by exhaustion, second one was disproof by counterexample. In section 2.5 we see an important method of proof which we call it direct proof. In a direct proof of a conditional statement which has a hypothesis P and a conclusion C, we first assume that the hypothesis P is true, and based on that we try to prove that conclusion C is true as a direct result of the assumption. So let's see how the steps of a direct proof looks like. Let's assume that you want to prove the universal statement for every x, P of x implies Q of x. Okay, so this is what we are going to prove. In the first step, you have to first assume that C is an arbitrarily chosen element of the domain, and the hypothesis is true for that arbitrarily chosen element. So in the first step, an arbitrary element of the domain has to satisfy the hypothesis, so that in the following step we prove the conclusion for that same arbitrary element. In the second step, we use the previously established results and definitions to prove that the conclusion Q of C is also true for that arbitrary element C that in the first step we assume satisfies the hypothesis. In the last step, in the third step, we simply conclude that the statement is true. Why? Because of universal generalization rule of inference. Because we have proved that proven that the conclusion is true for an arbitrarily chosen element of the domain. Therefore, the universal statement that we are going to prove must be true. This is the universal generalization rule of inference that we have seen before in the previous lectures. So in order to provide some example of direct proof, let's first define a rational number. A rational number is defined to be a number that can be expressed as the ratio of two integers in which the denominator is non-zero. In other words, a rational number is a quotient of two integers for which the bottom, the denominator, cannot be zero. For example, 3 divided by 4 or 5 divided by 7. So we are dealing with a fraction that both the numerator and denominator are integers, with the condition that the denominator cannot be zero. So the numerator can be either 0 or non-zero, but the denominator, the number at the bottom, cannot be 0. This is called a rational number. So here is an example of a direct proof. I'm going to prove that rational numbers are closed under addition. What does it mean? It means that if we have two numbers like r and s that are rational, then their summation r plus s is also rational. So here is the universal statement that we are going to prove. We are going to prove that for every r comma s, which means for every two rational numbers r and s, r plus s belongs to q. Q is the set of all rational numbers. So r and s are in Q. This is the domain of this universal statement. So if we know that r and s are in Q, the question is prove that for every r and s, r plus s is in Q. The assumption is r and s are rational numbers. The conclusion is prove that r plus s is also rational. So how can we prove it? We have to first assume that r and s are two arbitrary elements of the domain which is the set of all rational numbers. The set of all rational numbers is represented by q. Since r and s are both rational, therefore we can say this. We can say r is equal to a divided by b, and s is equal to c divided by d. Why? Because of the definition of rational numbers that we provided in the previous slide. So a, b, c, and d are all integers, but b and d, which are the denominators of the two fractions, cannot be 0. So they are not equal to 0. Now let's generate r plus s based on the algebraic operations that we know. R plus s can be written in the following way. Why? Because we replace r by a over b and we replace s by c over d. And then if you get a common denominator, you get this expression. R plus s is equal to ad plus cb divided by b times d. Since b and d are non-zero, therefore the multiplication of them, b times d, is also non-zero. So we find out that r plus s is equal to another fraction. The numerator is a times d plus c times b, which is obviously an integer because all numbers a, b, c, d are integers. And the denominator b times d is also another integer. Why? Because b and d are both integers, therefore their product is also integer. And they are non-zero because since b and d are non-zero, their product cannot be 0. So this means that r plus s is also a ratio of integers with non-zero denominator. And therefore, based on the definition of rational numbers, we can simply say that r plus s is a rational number. In order to see another example of direct proof, please watch the video in section 2.5 of the Zybook, video number 2.5.1, and also see the example of 2.5.1 in Zybook and see how we define another universal statement regarding algebra. In section 2.7, we define and introduce another method of proof, which we call that proof by contradiction or indirect proof. So the previous method was called direct proof. This one is indirect proof. Let's see what indirect proof is. A proof by contradiction or indirect proof starts by assuming that the theorem or the claim that you want to prove is false. After you assume that the theorem is false, then you need to show that some logical inconsistency arises as a result of this assumption. So you have a hypothesis and you have a conclusion. You first assume that the conclusion is false and then try to reach a contradiction, an inconsistency, a logical inconsistency. So here is the idea. In order to prove that if P then Q is a tautology, we prove that P and not Q is a contradiction. Why? Because if P then Q and P and not Q are negations of each other. Here is the reason. If P then Q is logically equivalent to the disjunction of not P and Q. We have seen this in the first chapter. And based on the De Morgan's law, not P or Q can be written as negation of P and not Q. Therefore, P and not Q is the negation of if P then Q. So we want to prove that if P then Q is true. Instead, we prove that P and not Q is false, because P and not Q and if P then Q are negations of each other. So how can we prove that P and not Q is false always, or P and not Q is a contradiction? If we assume that the theorem is false, which means if we assume that the conclusion is false, not Q, and the assumptions are true, which means P is true, then we must reach to a contradiction. In other words, we have to show that if P and not Q are true at the same time, then this is equivalent to a false, which means this is equivalent to always false. This is a contradiction. That's why we call this method of proof by contradiction. So we will see an example in the next slide. Here is an example of proof by contradiction. The question is, prove that if A and B are positive real numbers, then square root of A plus square root of B is not equal to the square root of A plus B. So we are going to prove this inequality is true. Since we are using the method of indirect proof or proof by contradiction, first we need to assume that the inequality is false, which means that we have an equation, right? So it means that for every two positive real numbers, the summation of their square root is equal to the square root of their summation. So this is the negation of the theorem. This is the negation of what we are going to prove. Now I have to try to reach a contradiction. How can I do it? Well, we say, okay, since this equality is true, we can square both sides. So if you square both sides and you simplify it by the algebraic operations that you know, the right hand side becomes A plus B, the left hand side becomes square root of A squared plus 2 times square root of AB plus square root of B squared, which means that A plus 2 times square root of AB plus B is equal to AB. If you simplify A and B from both sides of the equation, what we get is 2 times the square root of AB is 0, or the square root of AB is 0, which means that A times B is 0. We know that if the product of two numbers is 0, therefore either the first one has to be 0 or the second one has to be 0. So at least one of them is 0. This is inconsistent with the assumption that we said A and B are both positive numbers. When they are positive, they should be greater than 0. So none of them can be 0. That's in contradiction with what we proved. We proved that at least one of them has to be 0. So we reached an inconsistency, a logical inconsistency or a contradiction. Therefore, the theorem has to be true. You can see more examples of proof by contradiction in Theorem 2.7.1 in Zybook, and example 2.7.1 of your textbook Zybook.